maybe. Yeah, cool. So Chris, I was gonna say I saw that message in Discord. We got a couple of minutes. I might be able, if you want to hang out maybe afterwards, I could hop in there and we could poke around because I tried finding the repo that you sent and it didn't work.
Okay.
But
How does that work? Or
yeah, that's what I'm saying. We could go through the process to share in like a way that you could definitely send me a link that I could find. Um and all that and kind of like it might be
Mhm.
configurations on your side. You might be just grabbing the wrong URL from the wrong
Yeah.
place. Like there's so many
Well, I mean,
options in
that's
there,
the
man. Yeah.
URL I'm using to push to Git.
Right.
But
Right.
I probably did something in the background that's wrong because, I mean,
Well,
other than me pushing stuff up and I know it's backed up, that's about as far
yeah.
as it's gone. I've never had to share anything.
Which is
So I
excellent.
really
That's what
don't know
I'm
how to set that
saying.
up.
Yeah, dude, absolutely. No, I'm really glad you're trying because that's exactly what I want you to do. That's what Git is really for. So I'm glad you've been using it for your own evil purposes and keeping track of your version control like it is made to do. But then the collaborative part of it is the next step. So, dude, huge props for taking that step. I will absolutely make sure that you know how to do it. So, um, I just don't want to dive too deep into that right now, right before this next session starts, in case we run over. But
Nope.
just as a quick heads up for both of y'all, also, since you're here, we may have really low attendance today because, in case you didn't know, the presidential debate is happening the
Oh,
exact same
yeah,
time
yeah. I
as
was
our
wondering
coding
if
wednesday
that
Yes,
was
class.
going to
that's why I'm here.
affect.
Yeah, I appreciate that. I'm going to try to avoid making any direct comments about it, but I never watch those live, no matter who it is
Yeah.
that's debating. I always watch
This is
later.
something you'll actually get something out of.
So, but a lot of
The
folks did.
presidential debate's not going to be one of those things.
Again, our opinions about that we'll leave out, but there are several folks that did let me know ahead of time that they're not going to make it today because they prefer to watch the debate live, and that's cool.
Oh,
That's everybody's, that's their
Good, good
prerogative.
for good for them.
And that's what I say, man. Dig. It's part of the democratic process, and if you want to tune in live to it, go for it. So a lot of folks will be watching this as a recorded one. We may have a small number of us in the class, which would make it again a fairly. And today, both of you actually may remember because you were probably at this day for session one. Oh, it looks like we got some other folks jumping in, but
Yeah.
today, generally speaking, is going to be lighter-ish day. Like it was short last time. We have lots of room for discussion and stuff. So we have room.
I'm
So
still
Chris, the point being, we'll definitely have time to sort out the GitHub question that you had, even though it's
sure.
it's beyond the point of this class today. We'll definitely be able to, you and I can sort it out. And anybody that wants to hang out and watch that part as well, Michael, you're more than welcome to because
okay.
it's useful. It's relevant to where we get to the end. At the end of this course is where we get is the thing that Chris is doing. Gabriel, welcome. We are
Yeah, thank
just
you. Thank you very much.
yeah, yeah, man. Good to see you. Good to have you. We're just kind of chatting to
Thank
get going. Chris dropped. I don't know if you're in the Discord server, Gabriel, but Chris had just dropped a link in there for me
oh,
to look at. So we're kind of talking about that and seeing about how to access it. So a little bit later after the course today, he and I are going to discuss how to set up the thing he's trying to set up. You're welcome to hang out for that conversation. I will record that part too. Um,
okay.
but
Yeah.
don't feel bad if you get lost in that conversation because it's definitely for the end of this course and we get to where he's talking about. So it's going to be good to see if you don't know what the thing is. But
Yeah, it's cool. So my little daughter, she's just been all over, and it's just me and her at the house right now. So I'm just gonna be a little distracted.
oh man, I get you, dude. And I totally understand. How old's your daughter?
She's 15 months.
Oh wow, cool. Yeah, no, I know how that is. That's not an age that you can turn your back on her for even a second. I remember.
Right.
Yeah. So cool, man. I appreciate you showing up with that going on. And I trust me, I understand the struggle, man. My youngest is 2 or about to be 3, but you
Okay.
know, right there with
Thank you
you.
very much.
Yeah, man. Yeah. And I guess we got a couple of minutes before we like start. So anybody have any questions on anything up to now, or questions in general stuck anywhere?
Not really stuck. I
No.
have to review the different variations on classes that we
Mm.
went through yesterday. You
Okay.
know, I got all the pieces. I just have to put one over here, one over there, that kind of stuff. It's
Right.
a matter of practice.
Yeah. Yeah, and the thing that we ended with the classes with the different arguments and keyword arguments and stuff, that was really kind of refactoring icing on the cake sort of stuff. Again, we'll talk a little bit more about it today.
Okay.
But again, if you don't feel like you got a real solid handle on those things, I wouldn't worry about it. It's very good to know, but Man, I remember it took me honestly a long time to really understand classes. For some reason, it just felt like a thing I couldn't quite get a handle on until, like you said, you just got to play with them a lot, and you'll get it.
Yeah. Unfortunately, I have a job and I have people wanting stuff from me, you know.
Yeah, yeah. That's why it's really good to check out those things, especially Free Code Camp, that has classes lessons broken down into very short increments, or like 15-ish minutes.
Oh yeah,
Um,
yeah, I've been playing through those.
Yeah, those are I love those when I was really starting to learn and stuff like that, because I would find the same thing. I would just, I put it on my commute to work. I'd ride the train up into the city, and that was plenty of time for me to do some of those lessons. Or I'd find a few minutes like on a break or something. I'd go and do a few minutes of it, just sit down and do it while I was at work or something, and do it on like on the side. But
Yeah.
um
It's a lot more fulfilling than doom scrolling TikTok videos, that's for sure.
exactly. Exactly. You'll feel better about yourself afterwards for
Yeah.
sure.
And even better, you're not so mad at the world either.
Right, right, right. You'll have less hatred for humanity if you spend your time learning code instead of doom scrolling. I completely agree.
I'll be right back.
Yeah, for sure. For sure. We're gonna get started in just a minute or so.
I think I figured it out.
Oh yeah? Let me see. See what link you sent me. That might be it. So wait, is that the one is this the one have you been pushing and pulling through HTTP?
Yes.
Okay.
Actually, no, it's SSH in the background.
You're
There's
doing
a,
SSH? Okay.
yeah.
All right.
I think they've said that they've deprecated HTTP as a
They
link for that.
They have. I think you might still be able to set it up, but they always give you that warning. You're right. That says, hey, don't do this anymore.
Yeah, it's
That's
being done away with and it will stop working soon.
Yeah, it's
and
gonna
blah,
stop
blah,
working.
blah.
So don't. Yeah.
Yeah.
All right, cool. Well, yeah, again, Chris, we'll hang out and I'll make sure that we get that sort of nailed down to where it works the way we want it to. But we are right at 1800. So Robert's just joining, and Gabriel, Michael, Chris, thank you all for making it today. I mentioned this already, but just again for everybody that just hopped on and everything else, the presidential debate is happening tonight. So at the exact same time, it's actually starting right now. So a lot of folks have already said that they're going to be there instead of here. And if you didn't realize that and you want to go watch that, I wouldn't be mad at you for cutting out of here and going and watching that. It's completely your choice. You could watch this. We're going to record it regardless. But I do appreciate those of you that did show up, and let's dive in. So welcome back we are still in week 2. We're talking about algorithms and data structures this week. And today, on day 4, we're specifically going to focus the day on evaluating algorithms and data structures, and talking about how to choose data structures and algorithms as 2 separate things. When you're making the choice, what choice you are making, why you would make a particular choice. So we are going to do some hands-on stuff, but it's also going to be a lot more sort of conceptual things that we're going to do today. It is most definitely our heaviest computer sciencey sort of content today. It will be the most computer science like stuff that we do in the course. I also want to make sure to highlight that this isn't the kind of thing that you absolutely have to be super well versed in at a basic level. Some of this stuff is going to be higher level concepts that will be important if you intend to go and be a developer. But some of these things that we're going to talk about today specifically are going to be more like just to be exposed to the idea and understand what's happening there. So lots of time to ask questions. If you're confused on something or don't understand something or want a different explanation, please raise your hand, take yourself off of mute, jump in there. Before we go any further with stuff that we're doing, it sent out a problem set last time, the end of the last class on Tuesday, with algorithmic problems to solve, or about 20 of them. Did anybody get a chance to practice any of those?
No, I was
No.
studying the lesson last night.
Still studying the lesson? Okay.
No.
No. All right. Well, you all failed. Get out. No, I'm joking. That's totally fine. It's just there's self-paced things anyway. So when you get a chance to play around with them, do it. It's very good practice. The ones that we selected out there, the 20, again, those should be good entry point ones that are mostly focused on strings and lists and doing things with those at fairly basic levels and the mechanics of setting up functions and running them. And I have answers to all those. So if you do them over this next weekend or even later weeks down the road, even after the course or something like that, and you get to it and you get stuck on one of those, reach out to me. I'll send you the solutions to it, at least to get you unstuck, get you going. But those are a great practice tool if you haven't done any. And we've got some time today. We could, towards the end of class, once we talked a little bit about the content that we wanted to go through, since we'll likely have some extra time, we could go through and do a problem together, which we didn't really have time to do on Tuesday because it wasn't super crucial that we did. But if we have time today, we might do that if we'd like to kind of show an example of how to approach those problems. But if no one got stuck on them or no one had any questions about them, that's totally fine. We can move on. I just want to make sure that we set some time aside for that in case anyone did. I do want to quickly also acknowledge that I know this course has been really fast up to now, and it's going to be about this pace. It's going to be pretty quick. So today is a little bit of a slower-ish break. We're going to not do as much writing and stuff like that, but we will have some hands-on stuff. But I want to remind everybody it's self-paced, right? So if it's going a little quick, just don't drop out entirely. Raise your hand. Let me know that you're behind a little bit. I don't mind meeting with you one-on-one to kind of find out what it is that you're maybe stuck on or maybe want another explanation of. That's totally fine. So with that, let's go through a quick review on what we've done up to now. The major points that we've hit, we've covered a lot really in just the kind of 3 sessions that we've already done. One of the major things we've talked about is data. So one of the first places that we talked about in 2 sort of different senses. The first one is in the binary sense and how information is understood by our computers and how it's stored and saved in things like in memory and in storage. The difference there being what's persistent memory is something that's not persistent, doesn't stay from one session to the next, whereas storage is persistent and stays. But either way, it's ones and zeros. That's the data that's there. And then we talked about data types and how Python interacts with things like strings and numbers and lists and all those sorts of things. And we talked about a specific group of data types. Also, as far as review, our last time we were running our main.py file as a sort of simple application. And we had started doing import statements where we were taking classes that were written in a different file, but running through our main.py file and still doing things like making our car class. And we ended that session talking about the classes with a discussion about arguments and keyword arguments that were built in. And those themselves are lists and dictionaries to different data types that we talked about respectively. And we talked about how one is ordered, one is not ordered, and why you might use one over the other. We'll talk a little bit more about those sorts of things today. And again, so today what we're doing is we're going to compare and select algorithms and data types. We'll talk about what data types are, algorithms, and how you select them. And I'll make one quick note before we move on about next week, scheduling wise. Next Thursday is the 4th of July. So we're not going to have class on the 4th. We rescheduled that class to Monday. So be aware, we got class Monday and Tuesday next week. I know everyone committed to Tuesday and Thursday. So again, if Monday is a day you can't make, that's totally fine. We'll record it again and you'll catch up, but the schedule is going to be off. And I'll email everybody and put it on Discord and just make a couple of reminders to make sure everybody gets the message about that. Great. All right. So no questions about problem sets. Any other questions generally about the course, what we've covered up to now, or anything else? Or for anybody that joined the call recently, do you have any questions about the problem set if you tried them and got stuck? No questions? All right, then. Cool. So let's start with our first high-level concept that we really need to understand to talk more about the topic we're going to talk about today in choosing algorithms, and that is the concept of recursion. Now, recursion is a really fun idea. It's one of my favorite general things that exists. I love this idea, but you see it in a lot of different places, in a lot of different contexts. Generally speaking, it's talking about things that are self-referential or contain versions of themselves. So that might seem like a kind of esoteric definition, but what I'm going to do is exit this. I'm going to show an example of an optical recursion using Google Meet, because Zoom, like the call that we're in right now, has solved this problem and it won't allow you to do recursion like I'm going to show you right now. So I'm going to do is I'm going to start this meeting. I'm going to share my whole screen. And what's going to happen when I do this is it's going to hopefully not crash my computer, because that's absolutely a possibility. But when I share my whole screen, it is going to give me a warning that says, oh no, infinity mirror is what Google calls it. And this is just going to be a copy of my entire screen within itself over and over again, pretty much infinitely with no end. So I'm going to dismiss this error. It might hopefully doesn't crash anything. It'll give me a few seconds to show you this. But when I do, this is recursion right here. What you should be seeing is a full copy of my entire screen within itself, infinitely down to this little dot you can't even see. So you can see the cursor even being copied all the way down and everything all the way around. So this is optical recursion. So this is the same thing being repeated within itself over and over again. So I'm going to stop presenting so that we don't crash my stuff here. I'm going to go ahead and get out of this. So recursion is a really good thing to understand. We use it in other places. There are other places that we have recursion. We use it in language all the time. It's one of the things that makes human language different from animal languages. Animal languages don't use recursion, as far as we know. Dolphins might, but we can't study them very well. And we use it in things like sentences. Like there's no end to how long a sentence can be grammatically. You know, you can just keep making sentences longer and longer by adding more sentences to it, by saying like, I think that, or I heard that at the end of your sentence, and just keep going on endlessly. And there's nothing in the language that stops us. We have things in our culture that stop us. You know, you don't want to just keep droning on and stuff like that. But there's nothing about English or most human languages that stop us from recursively adding things into themselves, like sentences into themselves over and over again. Now, in computer science, when generally talking about recursion, we're talking about it in the sense of referring back to itself of like a function. So what I'm going to do is show an example of recursion. We're going to go back to our main.py file and we'll go through an example of recursion. But I want to highlight that this example and how we do it here and what we're going to do with it here can be done other ways. So this isn't a requirement to know how to do recursion. It's good to know. I mean, I think we all should know it. I'm showing it for a reason, but I'm just opening up our main.py file that we were using before. And if you remember, we talked about this control structure, a while loop. Recursion does very, very similar things. What it's going to do is run through a function over and over again until a certain criteria is met. And it'll, so much like a while loop. So we could accomplish a lot of the same things without doing recursion. But I want to show this as a sort of precursor to our discussion about choosing algorithms, because there's options, there's different ways to do it, and there's different reasons you might want to do this instead of doing a while loop. So there are uses for recursive functions. One of the uses is making games. There's a lot of times where you'll check a condition in a game, players' hit points or scores or something like that, and see if somebody's won. If they haven't, then run a function to run up to play around or something like that. And that's one place you might see recursion. This will become a little bit more concrete with an example. So let's run through a quick example of recursion. So again, today is going to be our most computer sciencey type day. It's also the day that's going to have the most brushes with math, even though we're not going to do it. I keep promising we don't need math for this course. You won't. But this is the kind of place where you might want to learn more math, and we might use some mathematical examples. They'll be very simple, though. So this first one for recursion is going to be somewhat mathematical. So we're going to do something that's called a factorial. And if you don't know what that is, or you don't remember, I had to look this up when I was first learning. I didn't even know this from before. But it's written as like a number and then an exclamation point. And it really just means you take that number and you multiply it by every number underneath it. So if we took 4 and we did a factorial of 4, it would be 4 times 3 times 2 times 1. So 4 times 3 is 12, times 2 is 24, times 1 is 24. So that's a factorial of 4. So what we're going to do is write a function that's going to give us a factorial. It's going to be an example of how we can do recursion. So let's do this function really quick. So we'll do it the way we've done it before with define, short for define. And then we'll just name something that we'll recognize it as. So factorial in this case, because that's what it's going to be doing. And it's going to take a number in that we pass it. So we'll give it a shorthand variable name here. Very common to use n for number inside of our parentheses, like we have several times anytime we define a function. Then colon to say that we're going to enter a new block in the definition of our function. So when we're writing a recursive function, what we want to start with is what's called the base case. And the base case is the point at which this will stop. So this is the stopping point for your recursive functions. You start by writing that first. And it's just going to be a conditional if statement. So it's going to check a condition to see if this condition is true. And we're going to check to see if n is equal to 1, because we want that to be sort of the bottom of it. But since we're doing multiplication, remember that factorial is the number times every number underneath it. We want to make sure that this does not get to 0. So if somebody puts in 0 or n happens to be 0, we want this thing to not give us 0, because anything times 0 is going to be 0. So if we allow this to get to 0, it will always return 0. So we want to check to see if n is 1 or 0. And in both those cases, we're just going to return 1. So what's going to happen is the function is called. It's going to take this input of n, which is going to be an integer. And it's going to check to see if that's 1 or 0. If it is, it'll return 1. So this is a function, but it's not recursive yet. It's not really doing anything that interesting. If we get any other numbers besides 1 or 0 in here, it's just going to look at us and not do anything. So let's put the recursive part. The recursive part is going to live in the else condition. So the other part of this control structure. Excuse me. So we're going to do, as we have before, else. And what we're going to do is immediately go to our return function. So we're going to return right away n multiplied by a function call of factorial again. Except this time, the input is going to be n minus 1. And that's it. This is a full-on recursive function. So this is going to return to us our factorial. And the way this is going to work is that when we give it a number, like let's say we gave it 4, like we did up here in the example. So let's imagine that this n is 4, and we call it. So it's going to check this thing, and it's going to say, no, neither of these conditions are met, so it won't enter this block. It'll go to else, and it'll say, okay, cool. I'm returning n times this function call. So this is 4 times, and then it'll call the function again with 4 minus 1, which is 3, which means that this return with 4 is just going to wait until this function goes through and does what it does. So it'll run through again with n as 3. So it'll check this and say, no, these conditions aren't met. Enter the else condition, and it'll do the same thing again with n being 3. It'll wait until. Yep.
Did you go over the part about I hit the 3 into the function definition factorial?
How it becomes 3?
Yeah.
Yeah, right here. So when the first time through, it's this n minus 1 right here is 3, because the first time through, everywhere you see n, the first time through is a 4, right? Every n you see is a 4 on the first pass through this. So when it gets here, it's going to be n minus 1, so it's going to be 4 minus 1. So this is going to be exactly the same as having, as calling factorial 3 the second time. So the first time through, all the n's are 4s. The second time through, all the n's are 3s. The third time through, all the n's are 2s. And each time it waits to return until this function is complete. So it's going to go all the way through from whatever number you give it until it hits this base case, and it returns 1. And when that happens, when this 1 is returned on the base case, it will return up all through each of those ones that was waiting. So it'll return all the way back through and give you the full total answer at the end. And that's how recursion is done. It goes through as many times as you give it.
Okay, so the line 33 provides a argument back to line 29, right?
Basically, yes. It's another call of this. So it's just saying, do the same thing. Do it again. Just keep doing it until this is met. So it's the same. Like we could have done this with a while loop. Remember, we had our condition that says, hey, as long as this condition is met, do this thing. This is really doing the same thing. It's saying, hey, as long as this condition is not met, basically, do this thing. So it's accomplishing the same thing as a while loop. And again, you don't have to do recursion to solve problems or to do things. You could do this with the while loop we already looked at, but it's in the sense it's doing a very similar thing. It's going through a number of times and doing the same thing each time. And this is how it's doing that. It's by referring back to itself.
So it's on line 33, it's basically doing that function call again.
Again.
Okay, I got it.
Yep. Cool. Everybody tracking? Anybody else got questions? Before we move on to showing this in action and see how it works. All right. So let's slide down here and let's run this factorial through the same process that we have before. I'm just going to run it directly in here. And again, if you have more than one console open somewhere, you should probably close it if you're following along, because we're going to need to, you can only have 2 consoles in the free version. But I'm just going to comment this stuff out. I could delete it, but now it's just not going to run. So what I'm going to do is I'm going to use the same idiom that we had before with the print, but we're going to call our factorial function. And let's do it with a couple of different things. So let's do it with 0. So we're going to test our base case scenarios of both 0 and 1. I'm just going to copy and paste these, make it a little faster, even though you're technically not supposed to repeat yourself. And then let's do it with something else, which we know, again, we've manually calculated for, so we expect the value of this to be 24 if we did our thing right. And then let's just see how it handles a bigger number like 10, and just see how that goes. So I'm going to save this, and then up at the top, I'm just going to hit this run button up here so that it should open up a console down here and run if I don't have my max number reached, which I don't. So it's going to take a second to load. All right, so here are our outputs. So we have 1 and 1 for our first 2 inputs, which were 0 and 1, that's what we talked about. That was directly putting in a base case. So it didn't even enter this else condition. It just exited out as 1. So that's good. That worked how we wanted it to. And then 24. So that's the output that we expected here for 4. And then here is the factorial of 10, which, I didn't calculate otherwise. I will just take its word for it. That looks good. But it didn't break at 10. So this is how you can make a recursive function. This is a recursive function in action. Does that make sense so far?
Yeah, yes, it does.
Anybody have questions yet? All right, so let's do one other thing with this, because if you remember last time when I wrote when we did the while loop and we took the count changing part out where we increment the count up and it just let it run forever, we got that error that said, hey, don't be a jerk, you're using up everything and other users can't use stuff now, right? It said something to that effect. We can rerun it again and see what that error was if we like. But let's see what happens with this recursive function if it gets an input that's way too big and goes too far. So I'm just going to drop a whole bunch of zeros in here. This is definitely going to be too much. And we're going to see what's happened, because recursive functions are slow. Recursive functions take a lot of compute power to do. They're not efficient. So this is probably going to put us over the edge. So I'm going to save this. I'm going to run it. And there we go. So it broke, but it broke differently. It says recursion error. Maximum recursion depth exceeded in comparison. So that just means this is just too much, that it went to, and I remember what I told you that every time it comes down here, it basically waits for this return. So this is waiting too long pretty much. And it capped out at some point and it just killed everything. So it's not the same error that we got with the while loop, but it is an error and it does stop. And there is a maximum amount of information that you could put in here without it breaking or before it breaks. Everybody clear on why that happened and how we got to the point of breaking it and what is going on here? Everyone have a sense of what's happening.
Overwhelmed.
What is overwhelmed?
Okay, you're
remember we talked about places that computers understand things, right? And there's storage and memory, and there's their CPU. So what's being overwhelmed by this?
I would say probably memory. You think it's memory? You can't process the calculation and store it fast enough.
Okay. Anyone else have thoughts on that? You think this is right? Is Michael right on that? You think it's memory?
It's a calculation power.
Yeah. Yep. That's probably too much, taking up too much of your CPU. And it could be maxed out the memory because you have to hold on to those things. So yeah, those are the things that are being maxed out, right? So it's pushing those parts of your system to the limit.
Okay.
All right, cool. So any questions about recursion as a concept,
I
as an
have a
idea?
question. It's just
Yeah.
something that occurred to me. Okay,
Sure.
scroll back up to the original. Yeah, okay. What if factorial was a negative number?
Oh, nice.
I've never tried that. I never
Yeah, I don't
thought
know.
about
I don't know. I think you should try that. You want to try it now? So later, I can try it
it.
down
Let's
here.
do it.
But this
Let's do
definitely,
it.
so this is definitely the kind of thing that I encourage you all to write it up to this point and do exactly that. Just try it out and say, like, oh, what happens if I put a negative in there? But I'll do that with you because I'm curious too. Same thing. Maximum recursion depth reached. Because so if you think about that logically, that makes sense because it's never going to get to this condition. It's going to go further and further away from 0 and 1, but on the other side of it,
Okay, yeah.
right? It's just going to, it already started below this number and it's just going to keep getting smaller and or further away from 1 on that on the number scale to the left, right? So, it's the same thing.
If you set your limit to some negative number,
You could,
Well, then
yeah, and
you
that's the thing
probably
is,
have to get into a logic where you're looking at if it's below 0, you're incrementing by 1, and if you're above 0, you decrement by 1. You'd probably have to play some sort of a mathematical game. I've never worked on negative numbers. I don't know if factorials allow it.
so what I would do, and it's funny because I think this similar thing came up last time, is that what I would typically do in this sort of scenario is look at one of two things. Either set up something to control the input so that it doesn't so that it won't give you an input that you don't want in this function instead of rewriting the entire function. Like this function, leave it as it is, but then control the input that goes to it to make sure that it rejects anything that's a negative number before it even gets to this. And then you don't have to change anything here at all. And that's like
if your number's negative, then
yeah. And what I would literally do is I would just put that in a separate function and then maybe add that function call within this function.
Or just say less than or equal to 0.
The idea being though is that I would want to separate kind of those concerns a little bit. It's a possibility of saying like controlling the input that comes into it versus this little piece of logic. That's one way I might approach solving that. The other approach might be that the recursion isn't the right way to do this. Whatever your issue is, this might be the wrong way, right?
Take the absolute value of it. And just
Absolute
remove
values.
the
Yeah,
negative
that's
from the
another
picture.
That's
Yeah.
another option. Yeah, exactly.
absolute values are always positive, right?
Yep.
Correct.
Yep. So that's what I mean. There's things you could do that would handle the input, and that would be sort of the idea that you'd want to do is like figure out in your application, in the context of what you're doing, what makes the most sense. If you wanted to say, hey, just flip this to absolute value, that'll work. Or do we want to just have like reject anybody that tries to put in a negative number and make them put in a positive number because we want them to know that it doesn't work with negative numbers or something like that, right? So this is similar again to the peanut butter and jelly sandwich discussion that we had about how there are several ways to do it and there's a ton of different approaches. And you got to decide how to do it. It's like as we're sitting here talking about this, like, oh yeah, we could do this. We could check the absolute value. We could separate somewhere else and see what the input is. We could change the logic here and do something else logically. Those are all different approaches and they all have different reasons you would do it. And that's great. I'm glad we're talking about that because that is the purpose of today's class is that you're always going to be making these decisions, deciding what to use and why, right? You don't just randomly use this sort of recursive function because you think recursion is cool. Even though I do think recursion is cool, it may not be the best way to do whatever it is you're trying to do. So the main concept that I want to highlight with these things. So first of all, I wanted to make sure that everyone understands recursion because we're going to talk about it with the other things we talk about today. And I want to make sure that we understand just what that is when it's being done by other algorithms that we talk about. So understanding the concept of recursion, seeing that it's something that could be done in different ways. So it's a very similar thing to the while loop, but just done differently. And then highlight again that the selection and the choice that you're making is being done for reasons that should be clear when you make the decision, right? The sort of philosophical thing behind this that I added some stuff in the reading. I think it's really good. Down here in the free code resources, there's a reading list, and all this stuff is linked for free. There's some great stuff about Python generally to automate the boring stuff. There's some other Python stuff in here, but this Timeless Way of Building is one of my favorite books. Just absolutely awesome. It's written by an architect in the 60s from Berkeley. and it became like this cult classic for designing and building any sort of system or anything. But he's talking about in the book specifically buildings and towns and how they exist in an organic way. Like they could be either alive or dead in their feel to the design. But human beings do this. They build without having an academic top-down way of doing it. When you do it academically top-down, it ends up being kind of dead, right? So he's talking about the way you build something timelessly. This is a great, great, great book. And what's cool about it is it's set up like a manual for reference. And you could read it in like less than an hour if you go to the detailed table of contents. And it just has the most important kind of sections without a lot of the really deeper story. Just you can read that top to bottom, and it's really quick. But one of the coolest things about that, I highly recommend everyone just like take some time and flips through that because it's awesome. It's actually a 2-part book. There's a more like example of what he's talking about in his second book, A Pattern Language, which is also great. But if you just do one thing, spend about an hour or so on Timeless Way of Building, is totally, totally worth it. One of the coolest concepts in there, though, it's relevant to what we're talking about here, is that all design that you're doing is trying to come up with a configuration for your system, whatever it is, whether it's a building or a town or a software system, that allows conflict between different forces that arises within a context, allows those conflicts to resolve themselves. So you're coming up with a configuration within a context that's allowing conflicts to resolve. That's what you're trying to do. So putting that in the context of software and this recursive function versus a while loop, for example, or any of the algorithmic decisions we're making, is that there is no perfect algorithm. There is no best algorithm. There is no one single, always best way to do it. It's always, always, always going to be dependent on your context and what you're trying to do and what forces are in conflict in that context. So to put that in a little bit more of something concrete, I wanted to talk about a way that you can very cleanly and algebraically decide
burger. Done.
what
Little rare.
is
Little rare.
the
Eggs.
best. Hang on a
I already
second.
got your
Somebody
order out, so
is not
on.
on mute.
Okay. Over easy. Sure. Yeah.
I'm
Thank
gonna
you.
mute them real quick. Sorry, someone was discussing dinner, not on mute. So, we're gonna look at a way that you can assess algorithms and decide which is best to use. And the same thing for data types, or not data types, data structures. We're going to talk about the difference between data types and structures here a little bit too. So it's kind of a third way we talk about data, talk about structures. Now, the way that we do this, the way that we talk about something being being more complex or more simple, is something called Big O notation. Now, this is the kind of thing that if you're gunning to be an actual developer and sit in the seat of developer someplace, especially at a big company, you most definitely need to understand this inside and out. If you're not trying to be a developer, this is the kind of thing that's it's good to be aware of. It's nice to know it's there, but it's not likely you're going to need it really that much, but you will see it places. So it's good to know what it is and what people are talking about. So Big O notation. The O actually was invented by like a German guy, so it stands for Ordnung, which means order of magnitude. And what it's doing is this chart is kind of showing Big O notation in a chart form. And it's on this left side, on this axis, we have operations going up this way, and then elements going here across the bottom on the x-axis. And what this is showing is the number of elements is the number of inputs that you have, and the operations is the number of operations that the computer is doing. So the lines as they go to the right are number of inputs going into an algorithm, and the lines as they go up are how long that thing is taking to process and do, right? Or how much space it's being taken up to store. So it's either how much CPU is being used or how much storage space is being used. And they're both thought of in terms of Big O notation. So I'm not going to go through and make us try to memorize any of these or calculate our own Big O notation for algorithms. It is something that you absolutely can do. There is a process by which you would calculate this. And if you go to those things like Code Wars and LeetCode in particular, and look at people's solutions and do those problem sets that we said, you may see people submit their solutions to say, hey, this is my solution. And they'll say, time complexity is O n log n, or space complexity is, this O, or what do they call this one? It's polynomial time, or exponential time or our factorial time, you'll see these things written, you'll see them referred to by name. So it's good to know what they are and what they're talking about, even if you don't want to calculate these on your own. And again, it's not required that you do. The main thing to understand here is that depending on what sort of algorithm you're using and it's big O notation, it'll go much slower depending on the number of inputs you put in. So this is very important when it comes to scale. To put this in some sort of perspective, places like Facebook or Google or any of those big companies are going to be dealing with stuff on the far right-hand side of this elements, this right-hand side of the inputs are going to be huge. There's going to be tons of people trying to access their systems, putting things up, comments, posting pictures, whatever it is they're doing. But projects like, say, Hired Labs, my project, is definitely not that size. We're down here on the left-hand side of the elements. So the algorithmic choices that we make in our development process are less impactful because they're way over here on the left-hand side in the lower left-hand corner. We're not going to have this huge number of inputs. But as you see, when you step to the right, it quickly becomes important what sorts of algorithms you choose, the more inputs that you put in. Because if you have inefficient code that does not handle things well and does a lot of operations, it's going to take all your computing power very quickly, or all of your memory very quickly.
So that you would use something like this experimentally to say, I chose this algorithm, this is where it came out on the chart.
Right. Yeah, that's a good question. So exactly. So then you're like 1 second ahead. I was going to ask if anyone had any questions. That takes us into our next thing. Does anybody else have any questions about this generally before I move in? Like up here at the top, I don't know if you can read it, but the color coding is, the green is excellent. So that's kind of what you're shooting for. The yellow greenish part is good. The yellow is fair. And then it gets bad up here in the O and log N, and then the red, the orange, those are bad. So generally you're shooting for this side, right?
So you got on the extreme left there, you have like one element, right? And it's such like a horrible algorithm that you end up in the red up there straight at the top.
Well, you see, the factorial was actually an example of the worst time. So factorial time is a way of saying the absolute slowest. And we saw that we broke it. We broke our factorial function with, we didn't really work up to a low input, but you could see that it wouldn't have taken us a lot to overwhelm that. To your point, it's very far to the left before that just shoots straight up.
Okay.
Right. So yeah, the number of inputs that it would take to do a factorial function and overwhelm a system is not that many. Low number of inputs, so that's inefficient. And so, yeah, the reasons that you would want to know how to do this sort of thing, again, is if you have a really large number of inputs, this is going to be impactful. So you're going to want to know how to do it. So if you know that your system, whatever it is going to be over here on the right-hand side, you're going to want to know that you're choosing more efficient things. Sometimes you can't. Sometimes you're just, you're stuck up in this area in the red because that's just the way it is. And you have to account for that in other ways, like running things asynchronously or, pushing off and spreading it out on different loads of different ways of handling it. Like, so there are options here, but sometimes it's just good to know where you are with things when someone does that. But Michael, to your question, one of the reasons that you would want to, again, when we're doing this in like a working phase, is kind of slide down here. And when you're making decisions, you're going to want to look at specific types of data structures or algorithms. So this top chart here is showing a set of common data structures. And then it is showing from left to right here at the very top, we got data structure. So by name. So this column is going to have a bunch of named data structures. And this is going to talk about their time complexity. So this is how long things take to compute in the CPU, right? So this is the time complexity section. They have an average and worst case here broken down for a number of actual function types they would do, like accessing information out of these data structures, searching for things, inserting things, and deleting things. And so it's measured on their relative speed for how fast they could be computed. And then also space complexity. This is the memory that's being used. So this sort of chart is useful because you can look at a data structure like an array. Now, array is the sort of broad computer science term for what we call in Python a list. So we've already looked at arrays. Lists are arrays. And you can see that accessing them is fast, but then searching, inserting, and deleting is not as fast, right? So this is color coded as well, but you can also look up here that we're looking between these two things. So the constant times is this 0 to 1. That's like setting variables as a constant time. and then O to the N is linear time. So it goes up, but there's like a close relationship between the number of inputs and the time that it takes to do it. So this type of data that we've looked at already, call it list, is one way of doing it. It has this sort of efficiency. These other two data types right below it, stacks and queues, we're going to talk about those today as examples of why this is faster or slower and how these are different from each other. They look, stacks and queues look a lot like lists when you write them in code, but they are structured differently and handled differently by the computer, so they behave differently as far as their speed for certain things. The other one that we've talked about, I'm going to skip a couple of these. I'm not going to go through all these data structures, obviously. But the other one that we've talked about already, and is very good to know, is a hash table. Now, in context of Python, that is a dictionary. And that is fast at a number of things. You see it's a lot faster at search and deletion in these average cases. And again, usually we talk about worst case because that's what's most relevant, right? That's what's probably, that's the thing you got to be planning for. So, but even at that, it's a little bit faster at some things than at others. But then if you're looking at the memory that it's taking up, it's about the same. So all this is to say that when you're making a particular piece of software, designing a system, you're going to be looking at the problem you're trying to solve, and then the system that you have and what's important to you. So again, if you're like, okay, well, I'm doing something with lists of things, I could use an array, a stack, or a queue. I'm going to talk about the stacks and queues and what choice you're making there. But you know there's a choice between these three. Let's just say you do. So then it's going to depend on what sort of thing you're doing, if you're going to be accessing, searching, deleting, and inserting, or if you care more about the amount of time it takes to calculate those things or the amount of space that it's taking. Because if you care about the time, then the choice might be relevant to you. But if you care about the space, it makes no difference. You could do whichever one you like because it's going to be about the same amount of space. So everyone clear on sort of what this chart is showing before we get any details and examine. Anybody have any questions up to this point?
So just the line below where it says average, worst, right?
Mm-hmm. Yep.
Those are different aspects of making a computation or making an operation, right?
Yeah, this is really just kind of different points on this elements line. If you think about that, worst to be, like the farthest right on this side. So if it's a huge number of inputs, it's what this worst case scenario is going to be. And it's going to be sort of the longest that it can take in terms of time complexity, or the most space it's going to take is the worst case scenario.
Okay, so the line below that where it says access, search, insertion, deletion, right? That's actual processes within the computation, right?
Yeah, that's things you're actually doing. So that's when you're trying to say access is getting something out of your array or list, as we know it in Python, right? That's access. That's grabbing something out of it. Search, that's looking to see if something is in the array, right?
Okay.
Insertion, adding something to it. Deletion is taking something out and not just looking at it, but removing it entirely.
Okay.
Cool. So this is an example of for data structures. And I'm going to talk very, very shortly about, explain the difference between a stack, queue, and array as an example of what data structures are and what that means and how it's different than data types. But this is also a way of talking about algorithms. So we've talked about algorithms as a high-level definition of what that is, and we've written a couple of our own. But this is another sense in which the word algorithm is used. So people will often talk about algorithms as a named thing that is a standard algorithm used for a certain purpose. So this list of algorithms here is just for sorting arrays. And you see there's a whole bunch of them, right? So that's just one kind of thing that you can do, that you can have a set algorithm for. Another really popular type of algorithm that you'll hear a lot about is search algorithms, sorting algorithms, and search algorithms. There are a bunch of them that people talk about frequently, by name. Out of this list, I think it's probably best to understand things like quick sort, merge sort, and bubble sort. But you can see the same thing. It's talked about in terms of time complexity with this has best, average, and worst case scenario, but worst is usually the most important. And then space complexity as well with just the worst case scenario and how much space it's going to be taking up. So that is big O notation quickly and in a nutshell. We're going to go through some examples to talk a little bit more about how these things work and demo a little bit of this and talk about how these decisions are being made and what's happening a little bit under the hood. But before we do, any other questions or anything else before we slide over to doing some typing and play around with the Python shell, which we're going to do soon. So if you're not ready to do that, we're going to be over in Python Anywhere typing in the shell in a minute.
Just wanted to point out a couple of things in the chat. We were talking about Michael was talking about negative numbers for factorial.
Yeah.
Something I remembered from another free trading course that I was doing a while back for a program is that it doesn't define for negative numbers.
Yeah, it
I
doesn't
don't know
work.
how
Yeah.
true that is now for
It makes sense. It makes sense because I mean, if you multiply two negative numbers together, then they're going to become positive. It's just, yeah, it makes sense if you think about the math of it. But again, this isn't a math course, so I don't really want to get too deep into how factorials work. I just want to show the example of recursion. But yes, there are mathematical reasons why negatives wouldn't work with factorials.
Yeah. And then the other one was just about recursion. I was looking it up on Python, and apparently there's a built-in limit for 1,000.
Makes sense. There's probably going
Yeah.
to push most systems to its limit at 1,000.
Yeah. And then I guess as far as doing any more than 1,000 or whatever the limit that they suggest creates a stack overflow.
Mhm.
Is that similar to like I guess a memory CPU overusage?
Yeah. That's it. It's a little further than we're going to get to in defining stuff like that. But yeah, basically just think of that as pushing the system beyond its limits.
Okay.
As Stack Overflow. Yeah.
It also breaks security because Stack Overflow is one of the exploits that you can have a set of code embedded, and as soon as you can overflow that stack, the CPU's restrictions around securities get overridden, and it's trying to execute its way out of its black hole, and it will execute your bad code under permissions that are unrestricted. So it's a common exploit that hackers use and other people.
A lot of security
Stack
applications
Overflow
for it. Yep. Good call.
Right,
but again, lots of stuff that it's a little outside of the scope of this course. But yes, that is for our intents and purposes here. We just know this is bad, and we don't want to use big inputs and recursion because bad things will happen.
All right.
Cool. Good questions. Any other questions or comments? All right. Nice. So we're going to slide over into our interactive shell in here. So where we have been before, and we're just going to do some Python stuff. So we don't need to do a whole new console. I'm just going to give us a little bit of space, even though I can't clear this out. And I just want to show some concepts, some things that were built-in methods with strings and lists, and then talk a little bit about how those things affect the decisions that we're making in our algorithms and things like that in a little bit of a practical sense. And then talk a little more, like I said, about those three different data structures, the array that we talked about, lists, stacks, and queues. So before we get into those differences between those data structures, I want to talk about some stuff that I mentioned towards the end of class last time that's relevant here. And that's the built-in methods and functions. So I talked about dealing with strings and lists a lot. And one of the things that we did with lists was where we said they are zero indexed. You could grab something out of them and look at them that way. Now, strings are very similar, that they're indexed. You could call them, look at things, pull parts out of a string in the same way. So if I had a string that just, let's say I define a string as this is my string. And then I could do things like call the first position. It'll just give me the first letter that's in there. And it'll return that. I can do things like slicing and take different sections out. This is kind of a cool function. So it's very similar to bracketing this stuff out and calling one piece, but I could call using a colon inside and then an index, say 4, and it'll give me everything from the one index to that last index, not including the 4 things. So if we count these 0, 1, 2, 3, 4 is a blank space, and it doesn't include that here. It just takes the first, all the indices before that. And I want to show something about this specifically. So again, keeping in mind that when I set this variable here, I'm just putting aside a named space in memory. So I've created a space in memory. I've labeled it as A, and I've told it that it's a string. And I've done a couple of things to it. I've like sliced it and taken some, looked at some stuff in there. But if I look at A, it's still exactly the same string. Nothing has changed. And if you remember, I talked about data types. Strings are immutable, are unchangeable. They don't change. So if I do on these sorts of things to it, I can concatenate strings. Another thing that you could do with strings. If I had another string, let's say set another string to another string. And then I could do things like concatenate them by doing A plus B, and it just sticks them together, right? So it says, this is my string and another string just stuck together with no spaces or nothing in there. But that hasn't affected A or B. That's not saved anywhere. If I want to save that, I have to, again, set this into another place. Then I can have that variable set like that. So the point here that I'm making is I'm showing that there are things you could do that are built in to strings, and you could do cool stuff with it. There's a split method that's built into a string. So you could do split and then give it a character to split on. So if I split on just empty the spaces, it'll give me the words in a list. So this returns a list of words, and then I could do things with that list. So this is something that's built into every string, and every string can do this. It's because strings in Python are really just kind of classes that have these methods built in, and this is a method of a string. So as soon as you make a string and label it in memory like we did, you could do these things with it afterwards. You can index, you can slice, you can split. But what's happening here is the original string that you set is not being changed. The memory is being set aside and saved as it is, and you're not doing anything because strings are immutable. So keep that in mind. Lists can do very similar things. You do very similar things with lists, but they are changeable. They're what's called mutable. You could change a list. So let's say we had a list. Let's do another example list of, I don't know, example list. And we'll just make something with just a few strings in it, arbitrary set of things to play around with a little bit. And so now we have these three things in here, and we could do things to this and add stuff to it and take stuff away from it. But again, I'm doing this not just to show you all the cool things that strings and lists can do, but I want to highlight some behavior and keep in mind that what is happening in memory. I want you to keep that in mind, because that's what we're talking about today is the choices you're making and what that is, because sometimes the code isn't going to look really different. You just got to understand how it's behaving and what's happening. So to reiterate, we've labeled a section of memory as example list, and we've given it this and said, okay, it's a list. So it's, again, computer science array, but it's a list in Python. Now, when these are stored in memory, this space is set. It's this length. All right. So we could do things to this list. It's changeable in the sense that we've said that strings are not changeable. The original string doesn't change. We could do some things here to change. So we can add stuff to this list. We can add things to the end of the list, for example, by using this thing called append. So you do dot append, open parentheses, and then give it something to append. So if we want to give it another letter to add, and then if we look at our example list, we can see that this letter D has been added. So now we have 4 elements in here. And what happened there is that this labeled space of memory has now been changed. But what that means under the hood is that this whole thing was just a new set of memory that was created with this same label. So this space of memory was set at 3. And the second we made it larger, the computer picked up this entire set, this entire thing, and found a space in memory that was 4 big. It didn't just make this bigger. That's not how lists work under the hood. So understanding that lists operate this type of data, this data structure of an array operates this way pretty much all the time in every system. This isn't just Python. Arrays are set aside in memory as a fixed length. So no matter what you do to them, although technically they do change, any change you make is picking up all of the entire array and putting it somewhere else in memory to fit the new size that you have. All right. So you could do all these things. You add something to the back. You could take something off the back using what's called pop. Whoa, pop. It's 1-0. And then it just throws out the last thing. And I didn't save that anywhere. You want to highlight everything. But we can see that it has been removed because now we're back to just 3 elements. So I didn't save this last element anywhere, but now it's gone. It's no longer in this list. And that's using pop. So that pulls something off the back. So you could add things to the back with append. You could pull things off with pop. These become relevant soon when we start talking about stacks and queues. But just keep in mind, you could do these with lists, right? You could use arrays to add things to the back, add things to remove things from the back. You could do similarly with the front. You could put stuff in the front. So I showed you up here, if I scroll up just a bit, with this string, when we did was called slicing, and we used this colon on the inside and then put an index in there. You do the same thing with a list. So let's slice this list up to, let's see. So we have 3 elements. So let's say we wanted to, if we just wanted to get the first element that's in here, we would slice up to this one because slicing is not inclusive. It does not include the last index that you give it. So I'm going to give it index 1, which is the letter B, and that will return just this, A. Right? So we could do that, and then that didn't change our underlying value. That just pulled something out. We didn't save it. So this is just a way of looking at it. Slicing is just having a look. We didn't change the underlying data at all. But we could use slicing to add something. So if we do example list, and then we do the slicing again, except this time we put the index to 0, and then we tell it to be something. We set it to something, right? So let's just set this to Z and imagine that it's kind of wrapping around. And now if we look into our example list, see that Z is at the very beginning. So it's right there at the beginning. Right? Okay. So there's
Well,
other
I have
ways
a
we can.
question.
Yeah, go ahead.
Okay, scroll up a little bit up there where we can see the original list, ABC, right?
Yep.
Okay, now you add a D, right? And the example list with a D is now in a different place in memory, right?
Yes.
Okay, what happens to the original list with just ABC?
Oh, that's a good question. Yeah, no,
Is
that I'm fairly certain is just thrown out because this is in memory, so it's not persistent in the first place. So if you don't tell it to stay somewhere, then it
No.
won't. But append does the operation what's called in place. So it does it to this array. It doesn't do it like separately. You know what I mean?
Okay, so it's like it's modified and moved, and then the original one just disappears.
Yes.
Okay, all right.
Good question. Any other questions?
One of the things I think I've seen before is that there's actually this awful looking hex code that is actually tracked as your list. And in the background, it's using that. And when you create the new list or move the new list, you get a new hex code, which probably somewhere in the system equates to a memory start location.
Yes, it does.
And then that becomes your new, the ordinal that it's pointed to, or I forget
Right.
what the term is exactly.
Yeah,
but
we
there's
don't
a
need to get into
specific
that.
thing
Yeah.
it's looking at.
We don't need to get into that, like how technically and mechanically it's done. The key concept to remember is that when you change something in an array, if you change the size of your array, or you change something in your array, size specifically, if you make it smaller or larger, it's going to pick the whole thing up and put it somewhere else. And that's a costly operation. That's why things like insertion and deletion are not best done in arrays, because those two operations change the size of the array. And as you can see, those are slower than doing those same operations with a stack or a queue. Right? So the main thing that I'm showing here is that this right here, insertion and deletion, I'm showing how you can do that with an array. And then I'm telling you that this algebra right here will show us that it's not the most efficient way to do it. That if you want to do insertion and deletion operations, you might want to look at one of these other ones. That's the main takeaway. And again, the reason is under the hood, the memory's getting picked up and moved. But yes, to your point, if you looked at the way the memory was referenced, it's going to be some weird hex kind of thing. And then you'll get a new one.
Okay.
Everybody tracking on that?
I got it.
Yeah. Any questions? Cool. So then I was going to show real quickly. We're not going to implement with code, but I was going to kind of write out so there's some sort of visual example of stacks and queues, and hopefully kind of show why it would be faster a little bit. Not exactly why, but at least understand what they are and sort of why you would make a choice between them based on the context, and give examples of the context in which you would make that choice. Right. So this is, again, the main takeaway here is to know that it's slow, because when working on a list, it's going to uproot everything in memory and move it to another set of memory. And that's a costly operation. All right. So I'm going to go up here and just use this as text. It's not going to be actual code. We're not going to implement any of these things, but I want to show some examples of stacks and queues. We're going to start with a queue, right? So a queue can be represented as a list, right? So you can do these things. You can implement, quote unquote, a stack or a queue, both, with a Python list, right? For the reasons that we just talked about, you probably don't want to, because it's slower to do it that way than if you use a built-in what's called queue, but you would have to import that from a special collection. And I'll show you which one that is. But to conceptualize these things, I am going to use a list. And again, like I said before, the code that you write when you're doing this level of stuff sometimes doesn't look all that different. Like an array, a stack, and a queue, they don't look super different. They just behave differently underneath, right? So I'm going to write out these examples a little bit using a list. But let's imagine we have a line of people, right? So let's say that we got people lined up, and we're going to wrap this into a list so that we kind of think of it that way. But they're going into a movie theater, right? And the movie theater's closed. But when they go in and when it opens, they're going to enter from this side, right? So they're going to come in. The first person that's in line is going to go out of this line and go into the movie theater. And then as more people show up, they're going to enter this side. So they're going to add to the end of the line, and you're going to get more people coming in this way, right? So this, on this side, when people go adding to the queue, this is called in queue, to in queue something. There's too many UEs in these things. And then you DQ on the other side. Right? So this is going in and coming out. So when the way that you can refer to this setup is first in, first out, right? Because the first person that came in, person one, when this is open, is going to be the first person that comes out. So this is the structure as it's referred to. It's first in, first out. Data structure is a queue. The reasons you might want to do this in a software sense, that you might want to design a system that does this, or an application that you might want to do this, would be like a customer service type thing, where it makes a difference where someone has come to you and what time they came to you is relevant. So if these people all come in with a request and they have a timestamp and you want to deal with the first person that came in first, you would want to use a queue, right? So for the reasons that we talked about, if you're going to have a huge list of people and you're doing this at a place like, again, Google, that might have a whole bunch of people asking for a service request at the same time, if you use a list, you're probably going to break your system. So you're going to want to use a queue instead. And the way Python would do it is, again, you would import a different package and you would call this a queue. And the difference there is that Python will treat a queue that is set up like a queue with variable space in memory. So it keeps it flexible here, and it doesn't uproot everything and move it when you add something to the back and take something to the front or from the front. But a queue is specifically optimized for this setup, right? So if you are not intentionally trying to take out specifically the first thing that came in and you want to take out something else, a queue may not be the best thing you want to use. But again, it's good for a specific type of thing like customer service, or anything where the order of things coming in is relevant. You want to take the first one that came in. Cool. Does that all make sense about a queue? Is that clear? Any questions?
I get that.
Any questions about a stack or a queue?
Okay, is the queue there? I mean, you represented it like 3 people and a few dots, right?
Yeah.
Is there a size or a capacity?
Yeah, so that's what I was trying to say, that if this is a list, like imagine you wrote this with an array, and this is exactly kind of the crux of what we're talking about here. You can make this entire thing with an array. But if you use an array, it will have a fixed size in memory. It will be this size when you make it.
Okay,
And when the next person comes in, it's going to uproot this whole thing and move it somewhere else. But if you make a queue, It will not be a fixed size. It will be variable size. So the end will not be defined in memory, and it will be flexible and be able to move without uprooting the whole thing. So,
okay, okay, I see what you're
so
saying.
that's exactly the decision you're making, is that if it's relevant to you, that you're going to have so many people coming in the in queue side that you want there to be flexible endpoint, you should use a queue instead of an array. And don't use a list, because a list will be slow because it is fixed. Does
Okay.
that make sense?
Okay,
Cool.
thank
Any
you.
other questions? All right. All right. Cool. So then the next thing, similarly, a stack is another data structure that, just like a queue, could be done with a list. You can make a stack with a list. It's just going to be slow for the same reasons, that any changes you make to it is going to uproot the entire list and move it to somewhere else. Whereas if you use a stack itself, it'll have a variable amount of space in memory. So showing this example on how it's different from a queue and kind of to separate them conceptually, we'll use a list again, but this time our stack is going to be, let's say plates, like dinner plates, right? And we'll say there's one plate, there's another plate, and there's a third plate. We're not even gonna number these plates because it doesn't matter. The plates are exactly the same. These aren't people. So it makes no difference. This plate, that plate, it's all about the same. Imagine we're at a restaurant, right? And so there's like a dishwasher coming in here and adding plates here once they're clean. And also there is, say, a line cook taking stuff out of this rack of clean plates and grabbing one plate and cooking on and doing some stuff with it, right? So what's happening in this setup is that things are in queuing and dequeuing from the same side. So they're coming in and out from the end. Nothing's getting added to the front at all. This could be arbitrarily deep. It makes no difference. We're only really going to be grabbing the last one at any point, right? So this, just like the one above, is called last in, first out as a setup. So a stack is a last in, first out. Now, last time, I think it was Chris mentioned that we could have used the analogy of, like, say, a magazine in a rifle or something like that, and these could be bullets instead of plates. And that would be fitting for a veteran group, and I do think that's fairly apt. The only reason that I don't like that analogy is that it's a little bit less dynamic than this, right? Like, so you imagine if you're shooting and you're out on the range or something, you got your M16, you got a magazine in there. When you get to the end of it, you're gonna take that magazine out, get rid of it, and grab a new one. Unless you got somebody sitting there loading magazines for you, which I've rarely been in a situation to have that. Maybe if I've gone to the range with my dad when I was a kid or something, but usually that's not how it goes. This is a little bit more dynamic of an example where there's somebody washing dishes in the restaurant as it's happening and they're adding to it as things are coming out. And the software analogy where you might use something like this would be if you're writing say an undo function for writing text. Like if somebody's writing something and they want to hit, if you hit Control Z on your when you're like writing a text document, that function is using this sort of thing. It's a stack that's doing that because it'll track the keystrokes going in. So this would be keystrokes coming in. And then when you go to undo, it'll just step back through these things in a last in, first out scenario. So that's how you would do like an undo function in a text editor or something like that, is with a stack. And once again, to make sure we're really clear that these things can be done just with lists, but it's going to become relevant with the number of inputs you have if you want to choose a stack or a queue. So again, if we're looking at the size of project that I'm working on, or if like a hobby project, it probably makes no difference. You're probably fine just using lists and array, lists or arrays, depending on the language you're talking about. In Python, will be a list. And it's probably not going to make a huge difference to you. And you don't want to mess with just setting up queues and doing it a different way because it's a slightly different implementation, even though it looks roughly the same. If a list is going to get it done, just use a list. That's okay. So everybody clear on that up to now? Any questions on arrays, stacks, queues, and those as an example of the decisions we're making here? So I guess I'll go back to this little.
Okay, the ones that on the O chart, right?
Over here.
Okay. Arrays, stacks, and queues are, well, in other words, what I'm saying is there like subcategories that would define each one of these things in the list on the left? Like arrays, stacks, and cubes are similar, right?
Yeah. Oh, you
And
mean like a grouping of these together?
yeah, like a grouping. Yeah.
Um, these are kind of grouped in an order. Like these are all really related down to about hash tables. And then all these trees down here are different versions of trees. So it's roughly grouped
Okay.
like that. But
Okay.
and this is just again a very, very small selection of possible data structures. So many more out there
Okay,
than
sure.
this. But and there's also again, categories can be they're somewhat arbitrary, right? Like we could group these in a number of ways and on a number of criteria. But
Okay.
yeah. There are I did want to show it unless there are other questions. Other questions. So one of the things that's cool about this, though, and I want to show down here on the algorithms, is that all these names, and it's true about the data structures as well, but all these are links, they're hyperlinks. So if you click on one of these, it'll take you to the Wikipedia page about it. And the coolest part about that is you see over here on the right hand side, it has a visual, like an animation thing of that particular sorting or algorithm or data structure or whatever. The algorithm was really cool. So this is a sorting algorithm that is stepping through. This is called Quicksort. This is also a really popular one, but it's showing the process, and there's a recursive process being done graphically, right? So it's taking the section and it's sorting within that section, and it follows this process until the whole thing is sorted. So this is really helpful to kind of just picture what these things are doing and how it's working. But then there's also much more thorough explanations and definitions, and if you really, really want to dig into it, much more in detail diagrams and the math behind
Yeah.
it and some implementations here in some sort of pseudocode. And so there's a really good resource to help you in understanding these things and how they might be implemented, how they might be used in code. You see why we're not going to do a lot of these algorithms today. It's going to it would take a ton to actually implementing these things. And this is a little higher level than we need to be in this course. We just want to make sure that you're aware of these things and what are out there. And it's good to know a few of them and know what they are. The other type of things that I think is kind of worth mentioning that's not on this list is search algorithms, and there are a few that I just want to get you thinking about and understand that you can, without even getting into really deep calculations of complexity. If you understand the principle here and what's going on, you could think logically about what's going to be slower or faster if you kind of generally know what's going on. So there are major types of search that are used. Again, there are tons of algorithms that are popular by name for searching. But the three kind of big types of search that are really good to know are things like linear search. So linear search is if you take a list and you go through, or again, an array in broader computer sciencey terms, and you go through each element in that until you find the thing you're looking for. So when we talk about the best case versus worst case scenario, in best case scenario, the thing you're looking for is like the first or second element in that list, and it just takes practically no time at all. You find it. The worst case scenario is the thing is not in your list, and the list is really long, and the list has 1,000,000 elements in it, and the thing you're looking for is not in there. If you have to go through each single one of those 1,000,000 elements before you know for sure that you don't have it in your list, it's going to take a while. So a linear search is not very fast. So we'll just call that slow. A much faster way of doing it is what's called binary search. Binary search is a really cool approach. It's generally a kind of divide and conquer type algorithm, I think, to where it takes a list and it splits it in half and it tries to see if the thing that you're looking for is inside of one of those halves, and it throws out the one that's not in there. So a real typical function or capability in computer science is the reserved word in. I think we've looked at this before when we looked at lists and arrays and well, not arrays, lists and arrays are the same, but dictionaries and things like that. All the collections that we talked about as data types, you can use the word in Python to see if it's in there. So if we wanted to say like so our example list down here again that we had, we know we have Z, A, B, C in it. So if we say Z in example list, it should say true. And if we say F in example list, it should say false, and it does, right? So that ability to see if something just is in the thing, it doesn't find the thing specifically, it just sees if it's in there. And we're not going to go into how that works exactly, but it's something that pretty much every computer science thing could do, like any language is able to do that, right? So binary search leverages that common ability. And think about an old school, like actual physical paper dictionary, not a Python dictionary, but how those were laid out. First of all, they're ordered already alphabetically, A to Z. So the thing that you're looking at, the list you're looking at in binary search, has to be ordered first, has to be sorted first for this to work. And let's say you're looking for the word book or something like that. So the first time binary search algorithm will go to this dictionary. If it's English, then letter M is the middle. So it'll split the entire dictionary on the letter M. And it'll say, is book in the first half or the second half? And since it's in the first half, because it starts with B, it'll throw out the entire second half. And then it'll go to that first half, so A to M, and it'll cut that in half again. And it'll say, is B in the first half or second half of that split? It'll throw out the half that it's not in. And you see this is much faster than linear search because it doesn't matter how big of a list you start with, it's always going to cut it in half at each step. So each step gets faster and faster and faster. So this is a much faster way to do search, right? If you can get your stuff in binary, but it has to be sorted first, right? So there might be a reason that, again, we look at the sorting algorithms. You have to look at, say, okay, I got to sort it first, and then I got to search it. So maybe binary search isn't really that helpful because you have to sort it first. The by far fastest way of doing search is hashing, using a hash table or hash map, what we call in Python a dictionary. This is by far the fastest way of looking things up. So when we talk about, like, say, dictionaries as the broader sense of dictionary, looking up an actual word in a language, you think about it in modern terms, what do we do now? We don't go to a paper dictionary and flip through pages. We go to Google and we type in the word, right? So what Google is doing generally is it's mashing that word with its definition somewhere and just going and grabbing it out of something like a hash map, or in Python called a dictionary. So it just gets the key and returns the value. So hash maps, hash tables in all languages are that key value pair relationship that in Python is called a dictionary. So in other languages, it's called different things. Like in JavaScript, it's called an object. And you'll see very frequently, because this is so fast for looking things up, and this is the preferable way to the preferable data structure to use if you're going to be looking things up. There's something called JSON, or JavaScript object notation, that is an exceptionally common way of passing data around from one system to another, regardless of what language that system is using or operates in. So even though this is a JavaScript object notation, everything interacts with JSON. Systems send data through JSON all the time, and they look a lot like dictionaries. So this object, this JavaScript object, it looks like Python's dictionary. It's got curly braces, it's got the key, it's got the colon, it's got the value, and it's got the end curly braces. It's the same thing. And it just like a Python dictionary, it can hold other dictionaries, it can hold lists, it can hold any other data type. And the beauty of these things, again, is that you can look up the values by just directly grabbing the key. You don't have to iterate through each one. You don't have to do any splitting or anything like you do any of the other search things. So if you can get your data into a hash table, that's the fastest way you're going to be able to search it. So search is what you're doing. It's very, very good to do a hash table. All right, so that is the very quick, very high level explanation of what goes into choosing algorithms, why you would want to do it, some very brief explanation of different data structures. So we use data now in a third way. It's not types anymore. We're talking about structures, and how the structure of data we use, meaning what kind of thing is labeled in your memory, is very relevant to the performance of your overall system based on the number of inputs you're going to have. So with that, we have plenty of time for questions. If we have any questions, let's start there. Do we have any questions about anything that we've talked about? Your stunned silence is very reassuring.
Well, okay. So if you were doing this in a real world project, you'd have all these elements. Like show the chart below that one.
Sure.
Okay. Like you have a fairly complex project, right? you would have to balance all these different things.
Yeah,
You'd
you
have to
would, but
optimize
like,
between up in the array corner, the array axis versus splay tree
yeah.
deletion or something like that, depending on how complex your project was, right?
Yeah, and I mean, again, and it's the kind of thing you're doing, the kind of data you're handling, the kind of problem you're trying to solve, and the context in which you're trying to solve it, right? So again, the difference between a stack and a queue, performance-wise, if you look at just this chart, they're exactly the same.
Yeah.
But then if you look at why you would use a stack versus a queue, they're completely different in the sort of behavior that you want them to have and the kind of
Yeah.
thing that you would do with them, right? So it's never purely, like I said at the very beginning, there is no one algorithm that's always the best, and it's never purely one aspect that you're making the decision based on, right? So it's going to be all the constraints that you have in your system and the full context of what you're trying to do is going to dictate why you make a certain choice over another. And this big O notation is just one of the many tools that's out there. And again, it's only really relevant at scale, right? So if
Yeah.
you know you're not working on a big project, you probably don't even really need to think about this most of the time. But if
Okay,
you're writing
okay.
something that's gonna scale, or you're trying to make it ready for scale, and you're trying to optimize and make the most efficient, this is just a way to approach it.
Okay.
And again, for anybody who is looking to become a developer at a large company and do this professionally, this is 100% fundamentally stuff you got to know. This is really, really important. You have to be able to calculate your own big O notation for your own algorithms. And typically the way an interview would go is they'll give you a problem like in that problem set that I gave out on Tuesday. They'll ask you to solve it as best you can on the fly. And you're going to need to talk about it in terms of its performance, both in time complexity and space complexity. So you have two big O notation values that you're going to want to tell them when you do it. And then they're going to ask you if you could do better. And you may not be able to do better, but you have to know if you can do better or not. And so that's again a real world scenario in which this is kind of relevant stuff. Is if you know you're going to be working on a big project or you're trying to work in a big company where they definitely are dealing with huge numbers of inputs, you're going to have to know that. You're going to have to know if like show them that you know how to calculate this and you understand it and you understand the choices being made and you know that writing inefficient code is going to be relevant to something like Netflix, you know. Like the inefficient code that I write, I don't think anybody at Netflix would be impressed by it, right? They'd be like, that would never work because it would just break with the number of inputs that we have. But does that answer your question though?
Yes, yeah, that's exactly what I'm looking for.
Cool. Cool. Any other questions? All right. All right. So nothing really new to mess around with here. Again, this is something that a little bit higher level probably. You're not going to be doing a whole lot of beginning things with stacks and queues. There will be times though, if you start poking around outside of that problem set that I gave on either Code Wars or Lead Code, where the answer the answer is really going to be using a hash table or something like that. It's like that is knowing that that's the best way to do it is sometimes useful, right? Knowing what good use is for. Like for example, good use of hash table is counting things that are in a list. Like if you have a list with a bunch of the same elements, you want to see how many of each element are in there. Hashing that is really good because you can make the key the name of the thing, and then the value is the count of that thing, right? So, that's really the purpose of this. So this lesson with the stuff we did Tuesday should give you plenty of stuff to practice and play with over the next few days. As a reminder, on Monday, we are going to be doing class instead of next Thursday, right? So we moved our classes up. So we have Monday and Tuesday next week. And when we come in Monday, we are going to be starting on our actual web application. Oh, wait, I didn't save whatever I did here. So let's save that. I'm going to show you what that is real quick since we got a couple of minutes. I went ahead and set this up today to show as a quick example. And I'll tear it down again over the weekend. So we're starting completely from scratch. But this is give a little quick preview. So in Python Anywhere, we've done things on dashboard, consoles, files. Now we're going to slide over to our web tab and actually make our web application just right here directly. So if you've been doing stuff up to now, like in your own local environment using VS Code or writing this stuff out elsewhere, that's totally cool. And you are welcome to keep doing that if you want to. But when we do things directly in the web tab, it's going to be deployed straight to the web right away. So this is going to handle the deployment step. Like we're just going to do it right here. And that's so by the end of class on Monday, we'll have a web application that's live on the internet and ready to go. And then we'll just work on it over the next couple of weeks until the end of the course and refine it and make it better until it looks roughly like this right here. So this is what we're going for. It's gonna be a very simple website. It's got, you know, some GIF stuff that we grab online that's free. It's gonna have some simple navigation at the top. Have a couple of different pages that we add, and then our application is gonna be a to-do list. So we see this very simple to-do list. There's no tasks in there yet, but we can just see the tasks that are available. We can add a task. So we can say new task. We can give it a due date of, say, the beginning of next year, and status we could say it's complete or to do. And we see it there. You'll have our little details. We can update our task to something else. Change the due date, give ourselves more time, who knows. And then we can delete tasks. And it gives a little JavaScript warning that says, hey, you really want to delete that task? And we'll say, yeah, I do. I want to delete that task. And now it's gone. And so the reason we do this, the reason we do a to-do list, task list, is it's representative of any application you can make, desktop, mobile, doesn't matter. They all do the same things. They do 4 operations: create, read, update, and delete. The things I just showed you, right? Read is what we're doing right now. There's nothing to read. There's no tasks. But the create is the add a task. The update is changing it. The delete is deleting it, right? It doesn't matter what app you're using. If you're using, you know, LinkedIn or Instagram or Reddit, makes no difference. They're all doing these things too, right? It's pictures that you're putting up. It's comments you're putting up. It's your profile that you're adding or editing or deleting or whatever the case may be. But every application is this. So we do to-do lists because they're very simple. There aren't a whole lot of fields that we're going to add in our database. We're just going to have a title, due date, status. That's about it. So it's a really good learning tool to set this up. And once we have this built, and we have this fully built all the way to the end of the class, so stick with us to this, you'll be able to change this into whatever application you want to, right? So if you keep in mind that this title, due date, and status is representative of just about anything you want. This could be blog posts. You could make your own blog, and this could be blog posts and the date that you wrote it. And, you know, you could have a place where you upload pictures and do different things like that. Like this is seriously, the sky's the limit once you get this basic piece down. And that's what we're going to start building next week. So if there are no questions, or if there are, I'm going to stop sharing. But we can stop there, and everyone is welcome to hop off. We got about 5 minutes before the actual end. But anybody have any questions or last thoughts before we totally wrap? No, nothing.
See you Monday.
All right.
Go ahead, Michael.
No.
I'm still just trying to absorb how you redefined Big O. It's meant something different for a long time for me.
Really? What? How's that? What do you mean?
Well, PG version.
Yeah, preferably, yeah.
Oh, yeah. It's just a running joke between me and my wife about the Big O.
Okay, I get you.
Yeah, and
Yeah. This is
now
algebra. This is way more
Yeah.
like pocket protectors and
Yeah,
you know, math.
really defiling a memory here. I'm still trying to get over it.
You're welcome. All right. Any questions at all? If not, we can wrap it here, and y'all are welcome to hop off, and then we'll see you Monday.
Okay. Bye.
All right.
I'm good.
Good
Thanks a
job.
lot, y'all.
Thanks, Jeff.
See you Monday.
Yep. Have a great one. See you Monday. And then Chris, man, I'm gonna stop the recording, but if you wanted to, we could talk
Yeah.
about the GitHub thing for sure.
Sure. Yeah,
All
yeah.
right. Nice.